This is a report on the research Human versus Machine Intelligence, Assessing Natural Language Generation Models Through Complex Systems Theory, published on IEEE Transactions on Pattern Analysis and Machine Intelligence by Enrico De Santis, Alessio Martino, and Antonello Rizzi. We have all seen it by now, right? AI that can whip up an essay, a poem, even computer code that looks totally 100% human. And it's incredible, but it makes you wonder about something deeper. Is the language that AI creates really the same as ours? I mean, deep down, in its very structure. Does it have that same, chaotic spark? Or does it leave behind a subtle, invisible fingerprint that gives it away? Well, today we're digging into a fascinating study that found a way to do just that, to lift that fingerprint. So here's our game plan. First, we're going to tackle the big question that has researchers buzzing. Then we'll open up the powerful complexity toolkit they used. Think of it like an X-ray for language. After that, we'll get into the good stuff, analyzing the digital footprints they actually found. This will lead us to the core discovery of the in-between machine. And finally, we'll talk about why this digital fingerprint is a really big deal for all of us. Okay, let's dive right in. The main challenge here is that we might feel like machine-generated text is different. We might have a gut instinct. But gut feelings aren't science. To really get to the bottom of it, we need a way to measure the invisible architecture of language itself. Now, check this out. The philosopher Ludwig Wittgenstein said this almost 100 years ago, and it is shockingly relevant to today's AI. He basically argued that words get their meaning from how they're used in the real world, from their context. And that idea, which we now call the distributional hypothesis, is the exact engine that drives models like GPT-2. They learn by scanning billions of sentences to figure out which words statistically hang out with which other words. But here's the thing. Human language is so much more than just what word comes next. It's this beautiful, complex system where we take a few finite pieces, letters and words, and create infinite meaning. The real magic, the secret sauce, happens over long distances. When a tiny detail in the first chapter of a book suddenly connects to the big reveal in the very last chapter. These are long-range dependencies, and a lot of experts think this is the hallmark of real complexity. So that brings us to the million-dollar question for these researchers. Can we go beyond just reading the text and actually find a way to measure these deep, complex structures with hard numbers? Can we prove, with data, that there's a real, measurable difference between human and machine intelligence? To see these hidden patterns, you can't just look at the surface. You need a specialized toolkit, kind of like an X-ray for language. And the researchers didn't just pick one tool. They brought in a whole suite of them from the field of complexity science. So here's how they pulled it off. First, they had to turn the text into something a computer could analyze. They converted the words into a series of numbers, a time series that captures the rhythm and flow. Then, they unleashed their toolkit on that data stream. Each tool looks at complexity from a totally different angle. Zipf's law for the basic statistics, multifractal analysis for the deep structure, and recurrence analysis for predictability. Put them all together, and you get a really comprehensive digital fingerprint. Let's start with Zipf's law. This is one of those mind-blowing patterns that just shows up everywhere in human language. It basically says we're kind of lazy communicators. We use a few words like the and all the time, and then most of our vocabulary is super rare. If you plot this out, you get a really predictable curve. The exact shape of that curve is the first part of our fingerprint. Okay, next up, multifractal analysis. If Zipf's law is looking at the individual bricks, this tool is like a fractal microscope for the whole building. It zooms in and out on the text's data stream to see how patterns hold up over long distances. It's not just asking if there are long-range connections, but how rich and varied they are. Is the text simple, or is it layered and deeply intricate? And the third major tool is recurrence analysis. Think of this as a pattern scanner. It tracks the flow of the text to see how often it repeats itself or revisits similar states. This is super useful because it helps us measure if a text is deterministic, predictable and rule-following, or if it's more chaotic and free-flowing, like a real human conversation. So with this amazing toolkit ready to go, the researchers set up a really clever experiment. Let's see how they put it all into action. They basically staged a three-way comparison to analyze the digital fingerprints of three very different types of writing. All right, so in one corner, you've got human writing, but not just one kind. They took 80 classic novels, think creative, flowing, artistic language. And to contrast that, they also grabbed Linux source files, also written by humans, but super structured and constrained by the rigid logic of computer code. And in the other corner, the challenger, 80 texts generated by GPT-2. And the results started rolling in. The very first test, using Zipf's law, was already pretty revealing. When you look at the number that defines that word frequency curve, you see this super clear pattern. The creative language in novels has one distinct signature. The rigid logic of code has a completely different one. And GPT-2, it lands smack dab in the middle. It's already carving out its own space. Now, what's really wild is that the multifractal analysis show the exact same thing. This measure looks at long-range complexity, and once again, you see novels in one spot, the superstructured code in another, and GPT-2, again, sitting right there in between. A very consistent fingerprint is starting to take shape, and this, right here, is where it all clicks into place. When the researchers combined all the different metrics from their entire toolkit, from word stats to these deep recurrence patterns, the picture became undeniable. Boom! This table basically lays out the core revelation of the whole study. Just look at it. Across all these different independent ways of measuring complexity, like the Hurst exponent, which tracks long-term memory, or determinism, which measures how rule-following a text is, GPT-2 consistently finds itself in its own unique zone, somewhere between human creative writing and human logical code. It's not one or the other. It's something new. So here's the bottom line. AI text is complex, for sure. But its complexity is different. The analysis shows it's more deterministic, its patterns are more intricate but less random, and it's more likely to get kind of stuck in certain patterns. You could say it has all the structure, but it lacks some of that chaotic, beautiful freedom of the human mind. And these differences aren't just small academic details. No way. They're so clear, so distinct, that when the researchers fed this digital fingerprint into a machine learning model, it could tell whether a text came from a novelist, a coder, or GPT-2 with over 95% accuracy. The fingerprint is absolutely real, and it's easy to spot if you know how to look. And this really is the key takeaway from the researchers themselves. You can't just use one tool to tell the difference. No single measurement gives you the whole picture. It's the combination of all these different complexity metrics, the entire digital fingerprint, that lets us so clearly tell the difference between the human and the machine. Okay, so we found this fingerprint. So what? Why does this actually matter outside of a research lab? Well, this is far more than just a neat academic trick. It has some really profound implications for how we deal with our world, which is getting more and more filled with AI. I mean, on a practical level, think about it. This method gives us a powerful new foundation for tools we desperately need. We can use this fingerprint to build better content filters, to automatically spot fake news campaigns that are being run by bots, to help maintain academic integrity by flagging AI-written essays. It even opens up entirely new ways to classify and understand texts in general. But it's even bigger than that. This kind of work is a huge step forward. It's building a bridge between totally different fields: linguistics, artificial intelligence, and complexity science. It's giving us a deeper, more powerful quantitative science of language itself. We now have a framework to analyze the very core of expression, whether it comes from a person or a processor. And that leaves us with one last kind of mind-bending thought to chew on. This research gives us a perfect snapshot of AI today, but these models are learning, they're evolving at a dizzying speed. They're getting better and better at mimicking our complexity. So as that gap closes, as their digital fingerprint gets harder and harder to tell apart from our own, we're going to have to ask a much tougher question. What then is left that is uniquely human?